In the boundless abyss of deep space, thousands of light-years from Earth, amidst brilliant stars and dark nebulae, two enigmatic celestial bodies swiftly orbit each other, defying the classical laws of physics. The echo of their motion reaches us across thousands of light-years, though the bodies themselves are incredibly small by the universe's standards. Space-time distorts around them, causing even unrestrained photons to deviate from their predetermined paths. The flight of these objects is so rapid that time slows its pace for them, while titanic tidal forces crumple their surfaces, covering them in folds and cracks. This is a rare and astonishing spectacle, even by the standards of the infinite cosmos. So, let us examine it more closely. Thousands of light-years from Earth, in the constellation Puppis, in the distant past, two red giant stars are living out their final moments. Before our very eyes, one of them transitions to a new stage of stellar evolution. Its internal fuel is almost depleted, and the star begins to cool rapidly. The delicate balance between gravitational forces and the fury of thermonuclear fusion is irreversibly broken. Trillions of tons of stellar matter irresistibly rush towards the star's center. This process reignites an uncontrolled thermonuclear fusion reaction deep within the star. A powerful explosion tears the star apart, leaving behind a superdense core, heated to unimaginable temperatures. The force of the shockwave irreversibly alters the structure of the stellar matter, completely destroying its atoms. They compress into superdense material, generating countless neutrinos. In place of the destroyed giant, a tiny but incredibly massive clump of matter remains. Around it, the outer layers of the perished star scatter outwards in a grandiose cloud, transforming into a diffuse gas nebula. At immense speed, these layers collide with the other red giant nearby. This collision causes that star to flare up, much like its recently deceased companion. And as the echo of the double supernova dissipates into space, only a pair of enigmatic objects remain, almost imperceptible against the backdrop of the boundless cosmic void. This is how, as a result of a grandiose catastrophe, the extremely rare and unusual cosmic objects we call neutron stars come into existence. Currently, only a few thousand celestial bodies of this class have been discovered. This is a minuscule number compared to ordinary stars. To understand why they are so rare, we must study the evolutionary paths of stars. According to modern understanding, the life path of any star is almost entirely determined by its mass. If its mass is less than 8 solar masses, the star, after passing through several stages, transforms into a white dwarf at the end of its evolution. It is hypothesized that after billions of years, it will lose its remaining energy and transform into a hypothetical object called a black dwarf. This path is destined for more than 99% of the universe's stars, including our Sun. If, however, a star's mass exceeds 8 solar masses, its evolution follows a different path, ultimately leading to a supernova explosion. As a result, the star's outer layers are dispersed into the surrounding space, forming a diffuse gas nebula. At the center of the system, a supercompact and extremely dense object remains, the former stellar core. Its further fate also entirely depends on its mass. If it turns out to be too great, the core of the deceased star will be unable to resist the inexorable pull of gravity and will inevitably collapse into a black hole. However, there is another path. In cases where the mass of the stellar remnant is between 1.4 and 2.2 solar masses, a neutron star is formed. The forces of gravity within it destroy atomic nuclei, forming superdense neutron matter with exotic physical properties. For various reasons, neutron stars are extremely difficult to observe and study. First, celestial bodies of this class are exceedingly rare. According to calculations, for every 1,000 ordinary stars, there is only one such object. Second, they are very compact and emit virtually no light in the optical range. Therefore, before the advent of X-ray telescopes, it was impossible to detect these objects. It is not surprising that the first neutron star was discovered only in the year 1967, several decades after their existence was theoretically predicted. This discovery was greatly aided by an unusual phenomenon related to the law of conservation of angular momentum. Due to this effect, most neutron stars have a very high rotation speed, and the interaction of their magnetic and electric fields generates powerful bursts of radiation that repeat with very precise periodicity. Such objects are called pulsars, and they constitute the majority of neutron stars discovered to date. Their pulses are effectively detected by X-ray telescopes, even at distances of thousands of light-years. In total, more than 3,200 neutron stars have been discovered so far. Approximately 90% of them are solitary objects. The rest are part of binary and multiple systems. Most often, the companion of these cosmic bodies is a red giant or a main sequence star. However, in rare cases, it is another neutron star. This occurs when two similar stars synchronously approach the end of their life cycles, and the explosion of one triggers the collapse of the second. Due to energy loss during this transformation, the stellar core remnants approach each other at a very small distance, which causes their mutual speed to increase to enormous values. This is how, according to modern understanding, the astonishing system known as PSR J0737-3039 was formed. It is located at a distance of approximately 4,500 light-years from Earth, and is unique in that it consists of two pulsars located very close to each other. The first of them is 34% more massive than the Sun, and is distinguished by an incredible rotation speed. Each second, the object completes 44 rotations around its axis. The second pulsar is slightly smaller and slower. Its mass is 1.25 times that of the Sun, and its rotation period is 2.77 seconds. If we were to examine these objects more closely, we would find that their sizes are extremely small by cosmic standards. The diameter of each component of the system is no more than a couple of dozens of kilometers, which cannot be said about their mass, which is comparable to that of most known stars. A consequence of these factors is the incredibly high density of the matter from which pulsars are composed. To understand this matter, we need to look deep inside them. Using mathematical modeling methods combined with the theory of neutron star structure allows us to learn even what is hidden from direct view. The outermost layer of objects of this class is the atmosphere. However, for neutron stars, this concept differs significantly from the familiar planetary gas envelope, like those of Venus or Earth. For both components of the system we are examining, this layer is no more than a few millimeters thick. This situation is typical for the vast majority of neutron stars. However, the youngest and hottest objects of this class can have an atmosphere several dozens of centimeters thick. It consists of plasma, heavily ionized remnants of stellar matter. Primarily, these are hydrogen and helium atoms, but heavier elements are also found. The next layer is the outer crust, whose thickness can reach several hundreds of meters. Gravity in this region is not strong enough to overcome the electrostatic repulsion between electrons and protons. However, it is strong enough to destroy the usual structure of matter. Elementary particles here are mixed together, but they still retain their internal integrity. Several powerful forces act on the outer crust simultaneously, such as gravity, magnetic field, electrostatic repulsion, and centrifugal inertia. Due to their combination, the surface of neutron stars is under constant mechanical stress. Periodically, this stress erupts in the form of starquakes, titanic deformations of the cosmic object's surface. As a result, mountains a few millimeters high and cracks up to a centimeter wide form on it. These numbers may seem insignificant. However, under extremely high gravity, a mountain 1 centimeter high is analogous to Olympus Mons on Mars. If we descend even deeper, we will find that this layer has no clear boundaries and extends several kilometers into the neutron star. As we delve deeper into its interior, the pressure gradually increases, causing more and more electrons to be forced into atomic nuclei, initiating a reaction with protons. This results in the formation of a neutron, as well as a barely detectable particle called a neutrino, which almost immediately leaves the celestial body's interior, carrying away excess energy. In turn, beneath the inner crust lies the outer core, entirely composed of neutron matter. This astonishing substance consists of many tightly compressed neutrons, and its density is 10 to 15 times higher than that of an atomic nucleus. For example, our planet, compressed to the same extent, would have a radius of only 150 meters, and a cubic centimeter of its volume would contain several billion tons of neutron matter. In both components of the system we are examining, the outer core extends all the way to the object's center, but exceptionally large neutron stars, according to modern understanding, also have an inner core. Its structure remains a subject of scientific debate. According to one hypothesis, the pressure at the center of massive stars can be so great that it is capable of destroying even neutrons, forming hypothetical quark matter. Such an object is called a quark star. Other assumptions allow for the formation of hyperon or kaon cores, consisting of exotic matter with extremely unusual properties. However, all these astonishing structures remain hypothetical, and it is currently impossible to definitively prove or disprove their existence. If we consider the system as a whole, we discover several amazing and intriguing facts. First, calculations show that the pulsars in this system move rapidly around their common center of mass in moderately elongated and very compact orbits. Observations indicate that the average distance between the components is only 800,000 kilometers, which is almost 2 times less than the Sun's diameter. Due to such a small distance, the mutual speed of both objects is very high. It exceeds 300 kilometers per second, allowing the pulsars to complete a full orbit around their common center of mass in just 2.45 hours. Such rapid motion leads to a number of unusual phenomena, caused by the effects of the theory of relativity. For example, observations show that at the moment of the pulsar's closest approach, the rotation period of each of them temporarily increases by 0.38 milliseconds, after which it returns to its previous values. This effect cannot be explained by classical physics. However, the theory of relativity predicted it long before its practical discovery. This anomaly is related to relativistic time dilation, which becomes strongest precisely at the moment of the object's maximum proximity. Another clearly noticeable phenomenon manifests during mutual eclipses and is associated with the anomalous redshift detected in the spectrum of one of the pulsars. This is because the gravity of the component closer to us slows down the signal from the distant object passing by it. As a result, the radiation loses energy and its wavelength increases. It is also known that the orbits of these celestial bodies are influenced by their interaction. This is expressed in the fact that their point of closest approach, called the periastron, is constantly shifting. This phenomenon is called relativistic precession and has long been known to astronomers. It is usually observed when studying fast-moving celestial bodies. For example, Mercury's orbit shifts by 43 arcseconds every 100 years. However, the periastron of the binary pulsar shifts 140,000 times more significantly. Within a single year, it deviates from its previous position by a full 17 degrees. Thus, among all known stellar systems, pulsar J0737-3039 has the highest relativistic precession. If we set aside the dry figures and ponder hypothetical planets that might be hidden within this astonishing system, their existence, though unlikely, is still considered possible. Some objects, distant from the center, hypothetically had a chance to survive the devastating double supernova explosion. Others could have formed later. The answer to this question is complicated by the fact that none of the widely used methods for searching for other planets are effective for studying such systems. In any case, there is no discussion of the habitability of hypothetical celestial bodies in this system. The chilling cold and deadly radiation make them extremely inhospitable places. Observations show that this binary pulsar constantly generates gravitational waves, causing the distance between its components to steadily decrease by 7 millimeters each day. This phenomenon occurs in all physically bound stellar systems, but it is usually too faint to be reliably measured. This tells us that in approximately 85 million years, the pulsars will merge, forming a black hole. This grandiose cataclysm will become a source of super-powerful gravitational waves that will sweep through the entire Milky Way and reach other galaxies far beyond its boundaries. The flash accompanying the merger may, for a short time, become one of the brightest stars in Earth's sky. In any case, the echo of this devastating explosion will eventually fade without a trace into the infinity of the universe.